Welcome back. We're now at lesson 18C. We're going to actually back up and look at something from 18B, which we did not do as a class, but this is a modeling cycle. In the previous assignment, you either looked at M&Ms or dice or both, which were simulations. And the thing that we are finishing up in our quantitative reasoning course is talking about simulations, modeling simulations, modeling problems, and looking at a cycle to conduct those modeling situations. Here is a 6-step process where you have a problem, and then you're going to formulate a model and compute what's going on, and then interpret. This is what you did in your preview. You were computing M&M models and dice models, and you were interpreting them. We're going to move on further today to talk about validating and reporting, but you also reported out in your preview lesson. So in your preview, you could have conducted simulation A with M&Ms or simulation B with dice. And as you later looked through this lesson, they really just wanted you to interpret and talk about what model or models you think the M&Ms or the dice simulated, and then they asked you to write about it. So here's a demonstration or simulation that I did using the M&Ms, and here's the one that I did using the dice. In your preview, you were also asked to watch a video. It was an animation of population growth from a Population Connections video. So if you have someone standing close to you or that you can talk to by phone or in person, it would be really good right now to discuss with them what you saw in your M&M simulation or dice simulation or some thoughts that you had about viewing the video. However, the first part of this says in lesson 18C, the total surface area of the Earth is about 200 million square miles. About 71% of this area is water, and there are about 7.1 people living on Earth. Then it officially asks us, what were your observations after viewing the video about the growth in world population since 1 AD? So like I was saying, this would be a good time for you to hit pause and to talk to somebody around you or take a moment and reflect on your thoughts about the M&Ms, the die, this video that you saw, and the population growth, and how can we simulate that or other events. This is a great time to stop and think about that. Then it would be good to go ahead and read the objectives, go on and look at questions 2 and 3, and then come back and we'll actually walk through the objectives together. So by the end of this lesson, we're going to understand that data from real-world models can create linear, exponential, logistic, and periodic models. We're also going to be able to employ the steps of the modeling cycle and determine the model that best fits the data. So this table and graph are just past the objectives, and it mentions that they show the approximate world population at various time points since 1 AD. And you can look at this in a tabular form, or you can look at this as a graph. Question 2 asks us, which model would best fit this data? Linear, exponential, logistic, periodic, or other, and then justify your choice and think about the steps in the modeling cycle. Again, the modeling cycle is located in your in-class pages in 18B, and it looks like this. And it mentions that there is a problem. We're looking for some essential features, and we're going to try to formulate a model where we select geometric, graphical, tabular, algebraic, or statistical representations that best describe these relationships. We can compute, we can analyze and perform operations to draw conclusions. We can interpret the results of the mathematics in terms of the original situation. We can validate our conclusions. We can compare them with the situation, and then we can either improve our model, and I like this part. We can improve our model, or if it's acceptable, we can just go ahead and report. but we can improve and run back up and start somewhere and come back down and improve or whatever we'd like to do. But ultimately, we need to report out our conclusions, whether it was several trips around the moon here, and the reasoning behind them, or around the sun. And this includes some choices, assumptions, approximations, whatever we did to come to our conclusions. Maybe not in that detailed of a fashion using the modeling cycle, but on question 2, it does say which model could fit better, or do you think fits better? Some possible thoughts you might say are that the data we're looking at could be best suited for exponential, like right over here. Uh-oh, you see our increasing rate, disregard that one. Our increasing rate, and it's increasing at an increasing rate. It's not linear, it's not periodic, and it doesn't show any signs of coming up here and leveling off like logistic. We could also say, you know, it does look a little bit exponential, but we do not have, look down here. Do we have evenly spaced x values? Do we have values in here that we're reporting evenly? Or are there other things going on in between? In other words, if we selected some values, we don't find a constant ratio if we look back over here to really call it exponential. But it does look exponential-ish. And then, based on the video that you watched, eventually our population will strain the Earth's resources, and population's got to slow down. And so maybe in the long term, logistic model is going to be what is our best fit. Make some notes, and then you go on and answer question number 3. So welcome back to question 3. The table and graph below give a different view of the history of the approximate world population in billions. In this case, the estimates are at various time points since 1650. And so it's good to pay attention to what's going on in our graph, billions and approximate population. Part A asks, on average, what was the annual growth in population between 1930 and 1940? So looking here, we could calculate a slope, and years are most likely our x's, and y are most likely our population. And we would take one of our y's minus the other. And if we start down here, we've got to start down here with 1940 minus 1930. When we do some calculations, we end up getting about 20 million people per 1 year between 1930 and 1940. But then it keeps on going to part B and says, on average, then what's the annual growth in population? Annual growth, annual, here's our per 1 year, annual growth between 1970 and 1980. So looking at 1970 and 1980, we're getting again, our slope is, let's do 4.4 minus the 3.7 over 1980 minus 1970. And we're getting about-ish 70 million people per 1 year. Well, it's not growing linearly because 20 and 70 are not the same. But then it asks a question, what was the average annual percentage, and I can't read this part, during the growth of these two periods? And I need some more space, and that's not going to be enough. So part C, what was the average annual percentage? So I've shifted it up here because I'd like to keep everything on the same page. And this is going to be relative change. And so I'm going to take my ending number minus my beginning number. I'm getting 0.2 billion. And so if I move my zeros over or multiply by my 9 zeros, I'm going to get the 200 million. And in the denominator, I need to put my beginning number, which is 2.1, or 2 with the 9 zeros. And when I divide out and multiply by 100, I'm getting about-ish 9.5-ish%. But remember, that's not annual, that's for 10 years. So let me divide that by the 10 years, and I'm getting about-ish just under 1% growth for this decade right here. Let me grab another color and let's do it, because I think it says, yeah, between these two time periods. So now let's look at 4.4 minus the 3.7, and that's about 0.7. And so with it being about 0.7 billion, that's actually 700 million. And I need to divide it by the beginning number, which would be 3.7, but times the 1 billion, or 9 zeros. When I divide these and multiply by 100, I'm getting about-ish 18.9%. But again, remember, that's for a decade, and they're asking the average annual. So let me divide it by those 10 years, and I'm getting about-ish 1.89%. Part D says, when modeling phenomena that are not governed by laws of nature or physics, it's often necessary to add conditions to the model, that is, restrictions. In the case of the world population since 1 AD, an exponential model can approximate the population pretty well. However, it would not be reasonable to use that model for predicting the world population in the next several decades, or even next centuries, as conditions prior to 1950 do not have as much to do with future trends, but as much more to do with recent events, more recent trends, or more recent demographics. So it continues to say, let me get another color, that there is an obvious pattern change around 1950, so around right here. It is more obvious from the graph than from the table. And so everything's going along fine, 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 fine. And then it's going that way, not fine, 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 fine. It starts spiking up. So what happened during that time that you think may have contributed to such a drastic change? And if you think about the historic events, you would note that World War II occurred in the 1940s. The war, the events around the world war, including the baby boom, baby boom, caused a change in the population trend. Since World War II, the world has seen a stronger increase in population as technology, medical improvements, and other world events have enabled growth in what were lesser developed countries. So if you haven't already worked on question 4, go ahead and pause and work on this. And I just want to point out that we're going to be filling in the table, and then part B is going to ask us what model you think is going to fit this the best: linear, exponential, logistic, periodic, other. Justify your choice, and then be thinking about the steps in the modeling cycle. So up here, it is asking us to compute the average annual change in millions of persons per year, and then the average annual percentage change. And my suggestion, I'm going to start writing in numbers. My suggestion is that you do several of these until you're comfortable with the calculations, and then stop or continue as you feel so moved to do. Realize your rounding can impact what you're deciding on your model choice. So when we go to do the average annual change is going to be to take the ending number minus the beginning number. And if it's in millions, then we're getting about, that's the 0.7. Here are billions, 0.7 billions. And when we multiply by our 9 zeros, we're getting about 70 millions of persons per year. Now note this per year. When we subtract, we're actually getting 700 million. But remember, we want it not for this decade, we want it for 1 year. So in actuality, we're subtracting, and then we're dividing by 10 to take care of this decade. So the final answer in this column would be 70 million. And if you want to keep going down vertically, you can. For myself, I want to go ahead and go this direction because right here, the average annual percentage change, we're going to take the, right here, remember what we were doing a while ago? How we have to do the ending minus the beginning and divide by the beginning. But remember, when we do that and multiply by 100, we're actually getting the percentage for 10 years, and then we have to take the percentage and divide by 10. So you should be able to come up with about 2.3%. The next one, we're going to calculate and get 70 and about 1.9%. So this would be a great time to cut the video off, hit pause. Don't cut it off, just hit pause. And then do some of these calculations and make sure that you fully understand where these numbers are coming from. Like on the next one, we would get 80 looking at these two numbers and about 1.8% because we're trying to find annual per year. So we'll cut this off or pause at any time and then come back and check your answers with what I'm writing in here. And I'll finish this up. I'll go ahead and hit pause, finish this up, and come back and ask you about Part B. So now looking at Part B, which model would be a best fit for the population? When we are looking around at the numbers that we have just gotten, we notice that it's sporadic. But part of a modeling cycle is to look at what's going on, make some thoughts, some predictions, what we've been talking about, what you've seen, and can the population actually continue forever exponentially? And it does start leveling off, but notice it's also increasing, well, kind of down, kind of up, and then it's slowing down. And with it slowing down, that could mean it's tapering off to be logistic. And that's what I'd like to pick. I'd like to pick that logistic is going to be our best model. The average annual percentage growth is slowing. It's gone from our, starting right here, even at the 2 to 1.6, 1.4, down to 1.2. And this is suggesting that the model has changed from increasing at an increasing rate to increasing still, but at a decreasing rate. And so this change indicates that a logistic curve really may be the best model. This finishes lesson 18C. You need to check your syllabus and see what else you need to do for this week's lesson. If you're done, celebrate. If you're not, keep watching some videos. Our semester is almost over, so hang in there.